Yeah. Thank you very much to the organisers for arranging today's meeting. There are many really important connections between random matrix theory and machine learning, and I'm going to speak about some that I think are particularly interesting, but I'm not going to try and give a systematic overview of the connections. I'm going to be talking about work that's in a number of papers. There's some here. I'll leave the slides in case anyone wants to sort of have these references into them further. So let me start with some very basic ideas, which are probably so basic everybody understands this, but at least allow me to set my notation. I'm going to be thinking about data, which is given to me, which consists of tuples which are vectors X. Think of them as very large vectors. These live in R to the D. D we'll think of as large, and we'll have some. These might be images. There might be other sets of large data, and then there are some labels, and we're going to associate data sets with labels, target values, and so in classification, the set Y is very much smaller. So, for example, these might be pictures of animals. Y is the label attached to the animal, the species, and X are the pictures. So we have the data defines a function from a finite subset of R to the D. That's the data that I've put in to the classification set. And the task is to find a function which generalizes that, in the sense it maps the whole of R to D to the classification set, and so allows one to classify data that hasn't been, on which the function f hasn't been trained. And to be more precise, this is a bit restrictive. You really want to attach a probability to the data sets. So we associate a probability with the data, and then we'll do some training with respect to data drawn with respect to this probability, and we want the correlation between the data set that we've used for training and the original data set to be as large as possible. And one thing that one typically does in this world is to generate functions. These functions have to be highly complex because they're sort of capturing very subtle features of some of the data. The difference between some species can be really quite minor, even though the species could be really quite different. And so one wants to try and generate highly complex functions which can match the complexity of the data that one is trying to classify. And so one introduces sort of artificial neural networks, which are, I'm sure, familiar to all of you. This is where you take the original data, you act on it with a matrix of weight vectors, and then apply a nonlinear function, sigma, component-wise, and then iterate this. So you have a sequence of weight vectors. Every time you apply the weight vector, you apply a nonlinear function. And this is meant to generate sequence of functions f, which are highly complex, capable of being highly complex, and depend on a large number of parameters, the components of the weight vectors. And this nonlinear function is free for you to choose. Typical choices might be the ReLU function, which is piecewise linear. It might be the tanh function. It might be this function here. There are many choices you can make there for the nonlinear function. And so how do you do training? Well, you form what you might call a loss function, which is the distance between, some measure of distance between the actual data and the function that you're forming from this artificial neural net. And so you want to try and minimize this loss. You want to minimize the distance. If you like, this is a very high dimensional version of least squares fitting to a straight line. But here the line you're fitting to is certainly not straight. It's a highly complex function. So you're trying to minimize, and in this case, there'll be the mean square error between the actual data and the function that you've generated. and you want to tune your parameters to minimize that. And then once you've chosen the parameters that minimize the distance between this function and the data, you can then use those parameters to analyze other data sets and try to form a classification scheme from that. So this seems fairly straightforward and intuitive, and there's really nothing at all new here. The problem is that these functions, these loss surfaces that you're trying to find the minimum of, are highly complex. So these are not at all straightforward. This is taken from a paper that I found that tries to give a sort of cartoon sketch of what these loss functions look like. So imagine yourself wandering around on this surface. This is a surface in the space of parameters, the components of the weight vectors. You're trying to find the global minimum, which is here, but these surfaces have huge numbers of minima and saddle points, and so your ability to find the global minimum, at least if you can only look locally, is is made enormously challenging by the complexity of the shape of the surface. This is another picture which tries to capture the complexity of these loss surfaces. This is taken from this website, where actually you can find films as you fly over this surface. And what you see are these surfaces have vast numbers, as I shall make clear later, exponentially large number of minima and other critical points. And so your exploration of this surface, you may find very bad minima somewhere up and think that's the global minimum, and may be completely unaware that there's a much deeper minimum some distance away. So the complexity of the surface is what makes this a hard problem. So you obviously can't do this analytically. There are too many parameters. The surfaces are too complex. So you could, in principle, compute derivatives. It's conceptually simple, but it's in practice out of bounds. And so you can't sort of find where the minima are in a way that you might do in traditional calculus, and then try to solve this equation to find all of the minima and try to find the deepest one. That's simply not going to work. So the idea is that you explore the surface at random. You choose downward at every step. You choose a downward direction randomly, that is stochastically, and this is stochastic gradient descent. And so you explore this surface in that way. This method, stochastic gradient descent, is known to work in highly restrictive situations when the loss surface is much simpler than the ones I've shown you, but it certainly isn't guaranteed to work for the surfaces that I've used. I give you illustrations of. So these are surfaces where there are a vast number of minima, and it could well be, in fact, you might imagine it's highly likely you get stuck by your stochastic walk on the surface in a minimum which is far from being the optimal one, but you wouldn't know that without having non-local information. So you have no right to expect this to work. Basically, you're exploring huge dimensional spaces which are highly complex. You're trying to find a minimum. You'll find them everywhere. The difficulty is finding a really good minimum, finding the global minimum or something that approximates it well. So you might think this is a hopeless task, but the amazing thing is that it works. So in practice, this is an effective method. And the question is why. So I'm going to ask a number of questions. One question I want to focus on is why does this method work in practice? And to give you some intuition about this, I want to turn to an area of physics, which is, I'm sure, familiar to many people here, the area of spin glasses, because this kind of question has arisen in physics a long time ago. So spin glasses, you form a Hamiltonian, an energy function, which depends on certain parameters that will take to be random, and certain variables which you might think of as spins, but you don't need an interpretation of this. You simply have a function of some variables with some parameters that are taken to be random, and to each set of variables, this gives you an energy, and you want to find the minimum energy of this. This is the spin glass problem. And this is a famous problem in physics. It tries to describe why glasses freeze at a pretty standard, why they repeatedly freeze at the same temperature, despite the fact that the configuration of the molecules might be different in each case. And you're faced with the same problem. So this is a cartoon of the surface of constant energy of a spin glass due to Chiara Camarotta. So you explore this surface, but this surface again is highly complex. And this is only a two-dimensional sketch of a surface that might have many billions of dimensions. So you explore this surface, and your goal is, as you lower the temperature, to find the global minimum of this surface. That would be the in statistical mechanics, the point where you would reach the sort of some optimal point. But you might think again that this is hopeless. You explore this surface, there are many minima. Why do you often end up in a minimum, the freezing value, freezing temperature, which is roughly the same whenever you freeze the same substance? Well, one measure of the complexity of these surfaces in spin glasses is to count the number of critical points. So you can a measure of sort of how the surface looks would be how many critical points are there in total, and how many are there measured by their index. So how many are there if you specify the number of upward or downward directions associated with the saddle point. So Cn of u will be the total number of critical points up to some height, and Cnk of u will be the total number with an index exactly equal to k. And these kinds of quantities have been studied endlessly in the physics literature. Some papers that have been highly influential are those of Fyodorov and Aufinger, where these were calculated using techniques from statistical mechanics. And what you find is in these calculations, that can be done in many ways. I'm giving you just one set of papers where these are studied. What you find is that in typical spin glasses, the number of critical points grows exponentially quickly with the number of spins, the number of variables. And so as the number of variables grows, these have a vast number of critical points, and also a vast number as measured by different indices. So it might seem like a hope that these are too hopeless, these surfaces, too complex. But what you find is a remarkable property, and again, this is old material from the physics literature. Much of it developed in Rome, by the way. Many of these ideas developed here in Rome. So these functions grow exponentially quickly, but they have a particular structure to them. And this is that even though you've got exponentially many critical points, you find some sort of banding amongst them. So saddle points with higher energies look more like maxima. They have more downward directions than upward directions. And those with lower energies typically look more like minima. So even though you can find minima with high energies, they're extremely rare compared to the total set of saddle points or critical points with high energy. So high energies look more like maxima, at lower energies things look more like minima. And in fact, most of the actual minima have a very low energy and typically pretty similar low energies. So most minima band in a way that no matter which minimum you end up in, they have more or less the same energy. Now, I'm summarizing a vast literature here in a few cartoon words, but this is the sort of picture that's emerged from many decades of study of these spin glasses. And so the question is does this inform us in any way about the problem of machine learning? Complex surfaces, both problems have complex surfaces, both have problems where you're exploring the surface at random, and in both cases you're trying to find a minimum. And does the spin glass problem inform the machine learning problem? So to remind you, the machine learning problem is that we have a neural net, something like this, which generates highly complex functions. These depend on weights. We're trying to minimize, trying to optimize with respect to the weights to minimize the distance between this function and some specified data. And then we're trying to use that as a training for the neural net. And so the question which I've already posed is what lies behind the unreasonable efficacy of stochastic gradient descent? Well, there are various modeling assumptions you can make, which you might use to try and analyze neural nets in this way. I've listed them here, and I won't go through these in too much detail. These are the standard assumptions that are used in, or they are standard assumptions used in the machine learning literature. They obviously simplify the problem. They're taken to be the ones which simplify it with the least damage, so without too much loss of generality. Any one of them could be criticized, and you find criticisms in the literature. But this is a standard set of assumptions that are used to model loss surfaces. So components of the data vectors you take to be standard IID Gaussians. You assume that the neural net can be approximated by a sparser network, so that there's a lot of degeneracy amongst the weight values. The weights are in some sense ergodic. They don't have any special structure. So the weights that are unique within the sparse approximation to the network are uniformly distributed over the graph of all possible weight connections. So there's nothing special about the weights that you find. They lie uniformly on some hypersphere. So again, there's some ergodicity assumption about the weights. The activation function, the nonlinear function sigma, is twice differentiable and can be well approximated by a piecewise linear function. The ReLU function is exactly piecewise linear. The function is any other nice nonlinear function that you use can be well approximated by a nonlinear function. And the action of this piecewise nonlinear function is in some sense as a mapping ergodic. So most of these assumptions have at their heart ergodicity, that you're introducing that the neural network in some sense scrambles things maximally. These are all assumptions I say that you find as standard in the literature, or that any one of them you could criticize in practice. So now what one can do is use those assumptions to try to do what was done in the spin glass literature, that's to compute the number of critical points on the loss surface. And the remarkable fact is that under those assumptions, the neural network exactly reduces to a spin glass. So simply apply the assumptions from the literature, use the formula that I gave you that defines the neural network, and that simply becomes a generalized spin glass in a way that I'll make clear in a future slide. So you can use the techniques that are developed in the theory of spin glasses to find expressions for the number of critical points on the loss surface, either the total number of critical points or the number where the index of the critical point is specified. And the form of these expressions that you get looks as follows. It's the expressions, and I'll give you some examples later. If you count the number of critical points on the loss surface, therefore trying to specify the complexity of the loss surface, you get expressions which turn out to be simply averages over random matrices. And the random matrices that you get are real symmetric random matrices. So they're technically what's called the Gaussian orthogonal ensemble of random matrices. They're n by n matrices where you take the matrix to be real and symmetric, and you take the entries that are free to choose, so on the diagonal or above, to be Gaussian random variables. And this is a direct consequence of the assumptions that are listed earlier. Now, as I say, we will see that those assumptions can be criticized, and you might have reason to doubt this conclusion, which follows immediately from those assumptions. But I want to talk a little more about this before I criticize it. So the conclusion is that both the critical points, just as they do for spin glasses, grow exponentially with the number of parameters. So again, as you increase the size of the neural net, your data set, the loss function, the complexity grows exponentially quickly. And you can think of this connection to random matrices as, crudely speaking, meaning that the Hessian of the loss surface at a random point on that surface behaves like a random matrix. That's perhaps not altogether surprising. But as we'll see, it's not exactly a random matrix, and this changes the story slightly. So in fact, what I'll show is that if you follow the assumptions that I listed earlier and do the calculation, you end up with a random matrix plus a deterministic rank 2 perturbation, which happens to be absent for the ReLU function, but is present for all other nonlinear functionals. But anyway, subject to that, you find the same banded structure in the critical points of these lost surfaces, just in exactly the same way as was found for spin glasses. So this was first pointed out in a paper in 2015 by Choromanska, Jan LeCun, Gerard Benarus, etc. They did the calculation for the ReLU function, and they found that the complexity was exactly given as an average over random real symmetric matrices, the GEOE. That was criticized, that paper, because people said, well, ReLU is a bit special. What we started by doing was to think about doing the calculation in general, and then we found that for general nonlinear functions, so beyond ReLU, you always get an average over the GOE, real symmetric random matrices with Gaussian entries, but now you pick up this rank 2 perturbation, which is the price you pay for the generality. But as I'll show, that doesn't make much difference. The implications are that this banded structure means that these lost surfaces inherit, due to their complexity, a sort of structure that makes stochastic gradient descent work particularly well. So just as we found for spin glasses, critical points that correspond to large loss typically have a lot of downward directions. So you might find a saddle point in your stochastic exploration of the surface, but typically if you've got a large loss, that saddle point will have a large number of downward directions, so it's very easy to escape from. And as you go down, you find that the saddle points acquire more upward directions. They become more difficult to escape from stochastically, until you reach a level where, with probability 1, you find all the minima, and these have typically roughly the same loss. N is the number of variables in the problem. So it would be the size of the data set, if you like. So how do you prove this? Well, I'm not sure this is quite the audience to go through the calculation in detail, but I will go through it in a sketch to give you a sense of the techniques that are used. But I'm feeling that this won't be an audience who want to go away and do this calculation for themselves. So I'll go through this relatively quickly. So the other is that, as I've said, it's standard in the machine learning literature to think about activation functions that are well approximated by piecewise linear functions. And then it's a straightforward calculation that the neural net reduces to something that looks like this. So you're using the piecewise linearity of the nonlinear function, approximation to the nonlinear function, and it simply it comes out straightforwardly from the assumptions that I listed, that you have a linear part here that's stochastic, that comes from assumptions that the weights again have a Gaussian distribution, but then there's a deterministic part as well that depends on the derivative of the activation function, the nonlinear function sigma. And this, of course, is absent for the ReLU function because its derivative is 0 everywhere. So the details of the specifics of the loss surface are in this part here, the deterministic part. This part is the stochastic part, if you like. This is the part that says that the loss surface looks on many scales random. This is the part that says there is some deterministic feature to the loss surface, which is important in the calculations. You then use the Katz-Rice formula, which says that you can count critical points by representing, so the expected number of critical points is an integral, and the integral basically in physics language is a delta function that picks out where the second derivative is 0. So it's picking out from the whole surface the points where the second derivative is 0. Sorry, the first derivative is 0, and that picks out the critical points. You can use the fact that the assumptions mean the integrand is spherically symmetric, so you can choose where to expand your integral, and then you can compute the joint densities because of the weights were assumed to be Gaussian distributed. Because everything is Gaussian, it's very well known in the spin glass literature that simplifies the calculation enormously. So everything is governed by this covariance, which you can write explicitly here. And then you end up with some very explicit integrals where the Hessian, which appears in the integral, is simply a GOE matrix, a random real symmetric matrix, plus this non-random perturbation, which is a rank 2 matrix. Then it's pretty straightforward, using ideas that will be familiar to those coming from physics. If you're not from a physics background, these are just identities that make this kind of calculations straightforward. You represent the absolute value of a determinant as a ratio of this form. And then these determinants here, using ideas that originally come from supersymmetry, but this is just an identity in random matrix theory. These ratios of determinants you can write as integrals over commuting variables, which give you the determinants on the bottom, and anti-commuting variables, which give you the determinants on the top. Then you can use the fact that the GOE average, the average over the random matrices, you can perform exactly. You can take it inside the integral, and the average can be computed exactly because the matrices are themselves Gaussian. So these averages are very well known in random matrix theory. So here's an identity for the random matrix average you have to perform. So then you're just left with, so that you've already reduced the n squared integrals, which is GOE average, to n integrals, which are the integrals over the variables you've introduced to represent the determinants. These can be further simplified, again, standard techniques that I won't go through in detail, and you end up with an integral with a finite number of variables to which you can apply a steepest descent. And then you deal with the perturbation, with the rank 2 perturbation by expanding in that term, and you end up with expressions that give you formulae for the very explicit formulae for the number of critical points, either the total number or the number weighted by their indices, which again, you can specify the index, you can put that inside the integral, and compute the integrals in ways that I probably won't describe to this audience. They're standard in random matrix theory, but perhaps of less interest to those from outside. So the story is that using these methods from spin glasses, you can compute the complexity of lost surfaces, and complexity here means counting the number of critical points either in total or weighted by index, and you find a similar phenomenology that as the number of variables increases, the size of the data sets increases, these lost surfaces become highly complex. The complexity increases exponentially, which is what we saw in the pictures. They're highly complex surfaces, but nevertheless they inherit this banded structure, which means that if you've got large loss and you encounter a critical point, typically it'll be a saddle point with lots of downward directions, so stochastic gradient descent won't be too badly affected by that. And so in some schematic way, this explains why stochastic gradient descent works. If you've got large loss and you do happen to encounter a critical point, typically it'll have lots of downward directions. By typically, I mean with probability 1. There will be some that you find that will trap you, but they're exponentially rare. And then they'll cascade down to a level of loss where typically most of the actual minima reside, and they all have roughly the same loss as the global minimum. So that's the kind of picture that appears from this kind of calculation. But you can ask, well, to what extent should you believe this? And the answer is that people have been highly critical of this kind of modeling approach. And in fact, all of the assumptions that led to the calculation that I described are in some sense questionable. you can find examples of neural nets where perhaps they're not the best model. And the conclusions are not compellingly supported by numerical experiments. So initially there was a lot of excitement around this subject, and then people started to do experiments to test whether Hessians of lost surfaces really do look like random matrices, and they started to find data that were critical of that. So in particular, if you get a real neural net and you compute the Hessian at various points, and you ask, does that look like a random matrix? The answer is actually no, and in a very important way. So I was hoping there'd be a board here, but so in the absence of that, I'll just have to use my hands. Random matrices, in particular GOE matrices, the density of eigenvalues has a very particular form. This was known to Eugene Wigner. It's called the Wigner semicircle law. So the eigenvalues lie typically in a restricted range, if you scale appropriately between -2 and 2, let's say. And the eigenvalues sit inside that support between -2 and 2. They get denser towards the middle, and their density behaves like a semicircle. So there's a semicircular density, which is the Wigner semicircle law. Well, if you compute real Hessians of lost surfaces, their eigenvalues don't have that distribution. And so what's going on here? Is random matrix theory failing completely? Are the assumptions that were put in, which I emphasize, were not chosen for this calculation. They're standard within the machine learning community, but are they too simple to capture what's going on in this distribution of critical points? So is there anything to be salvaged from random matrix theory? So if you look at the Hessians of real lost surfaces associated with real neural nets, typically they have something that looks a bit like a semicircular density of eigenvalues in some range, so between -2 and 2 if you scale appropriately, but it's definitely not a semicircle. And also they have eigenvalues that lie outside that range, which you wouldn't typically find for a random matrix. And so you find these outlying eigenvalues. You find more eigenvalues than you expect in the middle of the around value 0. So you find more 0 eigenvalues than you expect, and you find outliers that lie outside the range of support that you'd expect from random matrix theory. So this caused a lot of people to criticize the model and if you like, lose hope. But on the other hand, if you do what a physicist would tell you to do with random matrix theory, it's not to look at the mean density, it's to look at the individual positions of the eigenvalues and see whether there's anything particular there. You find universality. So in fact, if you look at on the scale, not where the spectrum lies between -2 and 2, but if you look at the scale of the mean spacing between the eigenvalues of real Hessians from lost surfaces, they do match the GOE prediction. So on the large scale, the scale where you are looking at simply at the mean density of eigenvalues, they're different to GOE matrices. But on the smallest scale, the scale where you look at the positions of individual eigenvalues, they match precisely the predictions of random matrix theory. So the question is how to combine these two scales. On one scale, random matrix theory does a superb job, and experimentally that's verified now in many experiments. On a large scale, the scale of the mean the scale of the mean density, it does a rather poor job. So can you combine these two? And it turns out that you can. You can develop a realistic random matrix model which works at both scales. And again, those coming from a physics background will understand that the mean density is often not a universal property. It's the structure on the scale of the individual eigenvalues that's universal, where you expect random matrix theory to work. And we've understood for 40 or 50 years how to combine the two, how to develop a model that works on both scales with some particular features and some universal features. So the model that you can develop is not one that relies on the assumptions that I listed previously. It's more general than that. It doesn't assume GOE type behavior, random matrix theory type behavior. Instead, it makes some assumption about what the Hessian looks like, other than assuming it's GOE, a purely random matrix. And it combines large scale and small scale structure. So I'll tell you what the model is. You form a sequence in N. N's the large parameter. It's the number of, it's the size of the data set, if you like. You form a sequence of random real symmetric N by N matrices, not necessarily Gaussian, possessing some limiting spectral measure mu. So these needn't be GOE matrices, and it needn't be that we get the Wigner semicircle law out of this. We simply assume that you have a sequence of matrices that has a limiting spectral measure. You then form another sequence, separate sequence of deterministic real symmetric N by N matrices with eigenvalues here, which you separate out into P eigenvalues at the beginning of the spectrum, Q eigenvalues at the end of the spectrum, and most of the eigenvalues in the middle. So you assume that you can somehow separate the spectrum out in these matrices. You construct them so that you can have P eigenvalues at the start, separated by a bulk, and then separated by Q eigenvalues on the other side. And you assume that you have some decreasing function S, which takes the integers into the interval 0 to 1. Then the model you take, which I say this is well known to people who come from a physics background, is you take a model of a Hessian, which is this S of B, this decreasing function B. B plays the role of the batch size. So in an actual experiment with real data, you can't explore the whole surface. You have to take a large number of points, and B is the number of points you take, an experimental Hessian. So we'll form a model of the Hessian to be S of B. B is the number of points used to form an experimental Hessian times an X. X was this random matrix at the top there, though not necessarily Gaussian, and A is this deterministic matrix. So you can think of it that the A is the real Hessian that somehow you're trying to interrogate, and this is the noise that comes from the fact you've only got a finite amount of data. And B is the amount of data that you're putting in to form this sort of approximation to the actual Hessian. Well, in random matrix theory, we know how to deal with problems like this, where you have a deterministic matrix and a random matrix added together. And under the assumptions I've given here, you can solve for what the spectrum of H would look like. H is the experimental Hessian, the thing that would come out of experiments with real loss functions. And under the assumptions that the eigenvectors of X matrix here, the part that lie in the bulk of the spectrum exhibit unique ergodicity. That is, there's nothing special about the directions of the eigenvectors for the point that correspond to these eigenvalues in the bulk of the spectrum. You can find a model which does fit all of the data that we have. So it's a very good model for the data. It gives you a bulk, which isn't the semicircle law. It gives you outliers and tells you probabilistically where those outliers will lie, and it matches the data that comes from real experiments. So it turns out that there is a way to combine random matrix theory, more sophisticated random matrix theory than I described earlier, to give you a realistic model of a Hessian, and therefore a realistic model of what the loss surface looks like. And it seems to describe the experimental data accurately, both qualitatively and quantitatively. Now, I could describe this model in more detail, but I'm more interested to tell you about one application of these ideas. No, I don't see a clock here. How longer do I have? Oh, perfect, perfect. Thank you. I want to tell you about an application of this kind of model, this kind of picture of how the Hessian looks, to something that's become extremely fashionable in machine learning in recent years. And this is the problem of neural collapse. So I want to tell you how this kind of model that I'm describing fits very well with the picture of neural collapse that people have found experimentally in machine learning, and in some sense, in some idealistic situation, explains what's going on in that context. So what's neural collapse? This is a very important recent development over the last several years, and I can describe it as follows. In a neural net, we have a function which maps a data set to a classifier set. So I've changed it. So K here is the number of classifiers. It might be labeling different species. It might be labeling tumors as benign or not. So K is small and fixed and is the size of the classification set that we're interested in. D is the data set we're using to train the network, and it's thought to be large. So a neural net maps the data set to the classifier set. And you can view the neural net as having two parts. A feature map, which takes the initial data set. So you're repeatedly applying this, this nonlinear functional on the weight matrices. You apply a feature map, which takes you from the data set to the penultimate layer of the neural net. So P stands for penultimate, if you like. And then there's a last layer classifier, which takes you from the penultimate layer to the classifier set. Now, this seems like an odd way to split your neural network up. And I don't exactly know, I confess, what motivated people to do this. But if you do this, people have found experimentally some very interesting phenomena. So the parameters used to train the neural net would be, well, if we're using it to train some variant of stochastic gradient descent on the loss surface, there's some functional which you're using to train the neural net. That was, in the way I described it earlier, mean square error, where you take the difference between the data set you're training, the neural net and the data set you're training, and you simply square it and average over the data set. But it can be some other function of the distance between the data set and the neural net. And there are many other functions that you can imagine. You can imagine some form of entropy. So some function that's sort of logarithmic, that captures some entropy that measures the complexity of the data. So there's mean square error, or there are various others. I'm going to keep this general for the moment, although I'll make it more specific later. So remember, I've got my neural net and I've split it up into a feature map, which takes the data to the penultimate layer of the neural net. And then I've got a last layer classifier, which takes the penultimate layer to the set of classifiers. Define the following quantities. Let's take the feature map evaluated for a particular classification and average. And then let's average separately over all the classifiers. The neural collapse is essentially four properties that people have found experimentally that concern the feature map. So the vectors of the feature map collapse to their class means. So the idea is that the vectors, the eigenvectors of the feature map collapse to simply the average with respect to a given classifier C. So there's a huge simplification in how the eigenvectors look. They all converge for large neural nets to one vector. That's a huge simplification. Secondly, the vectors you get for different classifiers have a particularly simple form. They form what's called an equiangular type frame. So I'll give you some examples of this in a minute. In some sense, they're all as orthogonal to each other as possible. So this is saying, neural collapse is saying that something that looked like a tremendously difficult problem, if the data gets very large and you look at this feature map, it becomes a vastly simpler problem. There are vastly fewer parameters or free variables than you might have expected. Now, there's two other properties of neural collapse, but I think I won't have time to talk about these today. But for completeness, I've listed them. So neural collapse is a set of four properties of the feature map that you might think to be an incredibly complicated map, but which is much simpler than you might have anticipated. So the best way to illustrate this is with some data. This is from the original paper of Donahoe and Papian, where they first observed this. You have some data, which are the dots here. You apply a repeated action of the neural net, and the eigenvectors of the map H converge as training progresses, and essentially you just get, in this case, 3 vectors emerging. So the vectors converge, and they converge to a set of vectors which are in some sense orthogonal to each other, as orthogonal as possible. So this is the equiangular type frame. So the fact that these points converge to a small number of points is the collapse, and the fact that these become an equiangular type frame sees that these points, the points you're converging to, are in some sense orthogonal to each other. And this was an experimental observation originally, and it's one that I want to talk about in the context of the Hessian of the loss surface, as I described earlier. So there is a simplification which is often used in the machine learning literature. It's called the unconstrained features model. So the idea is that the feature map H, in some sense, is behaving very logically. It's a very complex mapping. So the unconstrained feature model says, well, if this is really an ergodic map, maybe we could treat these variables as themselves amenable to optimization. So rather than just optimizing over the weights that define the neural net, we can also optimize with respect to these variables, which are the values of the feature map within a given classification. So this is a model that comes from the machine learning community, as I say. It vastly simplifies the analysis because you've got more parameters to average over or to optimize with respect to. But it's treated to be a sort of serious model within the machine learning community. And within this model, neural collapse happens not just at the penultimate layer, but in any number. If you separate at any level, you find neural collapse. And this is again known experimentally. So I want to finish by connecting this phenomenon of neural collapse with the property that I described of the Hessian that emerge from the random matrix model that I finished with describing, the realistic random matrix model that we now have. So I want to describe a few results that I obtained recently with my students, Connell Garrett. And the first one is the following. If we take the deep linear unconstrained feature model, so we'll take the unconstrained feature model that I described, where we're optimizing not just with respect to the weights in the neural net, but with respect to the mapping points of the feature map. Then if you take a global minimum with respect to the loss surface, and here this is the mean square error loss surface, then the Hessian at that point has exactly the structure I was describing that comes from the model that we associate with random matrices, the augmented model, if you like. There's a bulk of the spectrum, and there are outliers, and the number of outliers is precisely k squared, the square of the number of classifiers. And again, this has been observed experimentally. So within this toy model of machine learning, this unconstrained feature model, you can prove that at the global minimum, if you're using mean square error, that neural collapse happens, and that the properties that I described are all realized. So you have a bulk, you have outliers, the eigenvectors do converge in the way that was described, and they're in some sense orthogonal to each other. So neural collapse is something that you can prove within this model, as in the sense that I've described here. So this looks very promising. Seems then that with this point of view of random matrix theory, or the augmented random matrix model that I described, that that does allow you to prove interesting facts about the unconstrained feature model in machine learning, and that it proves that neural collapse really happens. Great. However, the experiments that have been done in machine learning suggest that if you don't use least squared error, mean squared error rather, I called it, neural collapse still occurs, but it may not be optimal. You may find global minima that are not described by neural collapse. So I've told you that within the unconstrained feature model, if you take mean square error loss surface, then neural collapse is a theorem. But in real experiments, it's found that if you go outside mean square error and use a different measure for the loss, you will have a global minimum, but it may not be the one described by neural collapse. Neural collapse will describe some other minima, but may not be the global minimum. And so this is something that has been of enormous interest in the last year or two in the machine learning community. And it's again something that we can understand in the context of the random matrix model that I described. So it turns out that the issue is that if you go outside mean square error, the structure associated with the global minimum that's beyond neural collapse is what's called low rank bias. So you have a more low rank structure than you would have expected typically. And we can prove this for the unconstrained feature model. So if we take a cross entropy, I won't describe exactly what that is. It's a different formula for the loss function. If you take the cross entropy method of characterizing loss and the unconstrained feature model, you can prove that sufficiently large, if your size of your data set is greater than the number of classifiers, so if your problem's over-constrained, then you do have a global minimum, but it's not the one with neural collapse. It's instead described by another structure, and that structure is associated with this low rank bias. So in particular, if you take the cross entropy definition of loss and you use the unconstrained feature model, you can ask, why did people in experiments find neural collapse? So let me step back for a moment. You're doing an experiment with a real loss surface. People doing these experiments found neural collapse. I'm telling you that the global minimum may not be described by neural collapse. It is, at least in this model, described by other structure. Why do people find neural collapse? Well, the point is that within these models that I've been describing, these cross-entropy models involving unconstrained features, the global minimum may not be described by neural collapse. Many of the other minima might be, but those minima have a greater basin of attraction. So as you're wandering around your loss surface, if you do happen to find the global minimum, it's not one described by neural collapse. But with probability 1, you'll get to something that's a good approximation to the global minimum, and that will be described by neural collapse. So neural collapse is something you find typically, but you can prove it's not something that happens absolutely within this limited class of models. So let me draw a few conclusions. Ideas from random matrix theory and statistical mechanics appear very naturally because the loss surfaces associated with these neural nets are highly complex, and they look like the functions that appear in many other areas of physics where we're used to dealing with complexity. In particular, under certain assumptions, these loss surfaces really do reduce to spin glasses. However, those assumptions are oversimple, we now understand. It is possible, however, to augment them, to build in both the universal and non-universal features to get a model that combines those within a random matrix model. And if you take that point of view, you can start to understand properties of loss surfaces that have been found experimentally, like neural collapse, which has had a tremendously great impact on the machine learning community. You can understand when that occurs and when it doesn't occur, and perhaps why. So I think we've started to understand more than we did at the beginning, but I emphasize much remains to be done, and I hope that's why people are interested in the subject. Thank you.